Just a couple reminders. First of all, the last day to withdraw in here is Wednesday, November 23rd. If you feel like you are in a position where you are concerned about your status, please talk to me and I will let you know what I think. Really, I do let the decision whether to stick with the course or to withdraw, I'll leave that be up to you, but can at least give you some idea as to what the likelihood may or may not be for you to pass the course. A couple extra credit opportunities. These are experiments that appear in your packet. We will not be doing them in lab, but they are experiments numbers 11 and 12. These are take-home type labs. So if you were to look in your packet and check these out, Experiment 11, this is one that we call an egg experiment. This is one that involves a raw egg, and with that raw egg you are going to remove the shell from that egg using some vinegar, and then you will use either some corn syrup or honey or something to observe what happens to that egg once that shell is removed. The experiment itself takes 3 days, but when I say 3 days, it doesn't mean it's 3 days of continually watching. It means that you're going to take about 15 minutes each day to go ahead and do a few things and make some observations, and then write up your results. And then experiment 12, this one here is one that involves the use of red cabbage, and you'll be testing a number of household chemicals to see whether they are acids, bases, or neutral. The due dates for these, December 29th for experiment 11, December 6th for experiment 12, and if extra credit is important to you, you'll have them ready at the beginning of the hour. If it's not important to you, then you won't have them done by that point, because after 8 o'clock on each of these days, the opportunity to submit them will disappear. Each one of these is worth up to 2 points. Maximum extra credit for the semester is 10 points, and you will need to provide some proof of completion for these activities. And by proof of completion, you have your smartphones or digital cameras or whatever, take pictures of it, and of course you're going to put your face in the picture to make sure that you are the one that's doing it and that you're not borrowing somebody else's data. So again, you do need some proof of completion to show that you've completed it. And as far as what that proof of completion is, there is a links that you will find in the D2L Dropbox. So if you go to your lecture course, you will go to Assignments, Dropbox. It'll list these folders. Once you click on them, now for me it doesn't show it because I'm in here as a teacher. On your side though, you are going to see some description here as to where you'll find extra credit lab. If it's not in your packet, there's an electronic version that you can use in here. And again, you do need to provide some proof of completion. If not photos, then the experiments will also provide some tangible evidence for you to bring in and show me. So at the very end of the egg experiment, you will have an end result that you can bring in here and show me before class on the 29th. The red cabbage lab will also have some tangible product at the end that you can bring and show me, and that would take the place of any digital photos that you might have done. So any questions on the extra credit opportunities? All right, I think that takes care of that. Then let's see, what else do we have set up here? I guess we have our quiz. So coming in here on the quiz, it asks for you to check out the questions. Questions were to basically look at the names and tell whether they were carboxylic acids, ketones, or whatever. And so in order to do this, we need out, and I thought I had this, looks like I need to reopen this. So I'm going to open up the guide to nomenclature that you should have out right now. And we must have passed this out 2 class periods ago. And by the way, the answers for the organic worksheet that we have here are available on D12. So again, you can check out your answers. They are keyed to, it looks like November 8th. But we would like the handout available here. This one right here. And today we are going to wrap up our study of nomenclature of organic compounds. And when you look at the names, again, if it's an alcohol, it ends with OL. If it's an aldehyde, it ends with AL. If it's a ketone, it ends with ONE. And if it's carboxylic acid, it ends with OYC acid. So we are going to start with the models we had out here in front of the class the other day. And we are going to go through and name these. And I want to try to make sure I have them out in the same order that we looked at them here the other day. So we will start with this one. And then I had this one here. Then we had this one. And right here. And here. Now, for those of you that came in early, what is it that I have in this flask? What did I put in here? Again? Deionized water, exactly. And so what I'm doing here with this deionized water is I'm heating it up, and I'm going to let this heat and boil for about 3 or 4 minutes. And once we get up to about 3 or 4 minutes, then I'm going to go ahead and remove it from the heat and set it aside. So again, in order for me to do this demo, I need you to understand that I put water in here, and that in order for it to work, I need to heat it for about 3 to 4 minutes. What I'm trying to do in here is to replace all of the air that's in here with water vapor. So the only thing I'm going to have inside of here is water in the liquid phase and water in the gaseous phase. And by boiling this long enough, any air that's in there should be replaced with the water vapor that's being produced. So with that said, we're going to go through the nomenclature of these molecules that we have up here, and let's just do a very quick refresher as to how we would classify them. This first one, oh, you know what? I have these also on the, I believe I also have these in here. Let's see if I do. Today is the 15th. So, models, here we go. Oh, and I got names in there, so we don't want that. So never mind. We'll come back to here, and we'll look at the structure. And first of all, if we look at the structure of this one, how do we classify this molecule? This one is a carboxylic acid. It's a carboxylic acid. So now, in order to name this, we are going to go back to our nomenclature rules, and we pull out those nomenclature rules right here. We are now going to name a carboxylic acid. So in order to name a carboxylic acid, we count the number of carbons that is in here, and then we name the alkane that has the same number of carbons. So an alkane with 3 carbons would be called what? What do we call an alkane with 3 carbons? What is the prefix that stands for 3 carbons? Prop. So here's our molecule. It's prop. And so the alkane would be called propane. So now if we drop or follow our rules, the rules say that if it is a carboxylic acid, what we're going to do is we're going to drop the letter E from the alkane name. As a carboxylic acid, we are going to replace that E with the suffix of OYC acid. Drop off the E, replace it with OYC acid, and we call it propanoic acid. This here's propanoic acid. We go to the next one. This one here, CH3, CH2, OH. How do we classify this one? In case you forgot, pull out your classifications. We went through this one's an alcohol. So next thing we're going to do, if it's an alcohol, it says we count the number of carbon atoms in the molecule. In this case, there's how many carbons? There's 2 carbons. And tells us then we write out the name for that alkane that has 2 carbons. So the name of a 2-carbon alkane is ethane. And then if it's an alcohol, what we do is we drop the letter E from the alkane name and we replace it with the suffix of OL. And then it says that the position of the hydroxyl group is numbered if there are 3 or more carbons. There's not 3 or more carbons, there's only 2. So we come back to the name, we drop off the E, replace it with OL, and this is ethanol. Okay, and I think I've heated this thing here long enough, so I'm going to go ahead and remove this from the heat. This is for a demo later today. I'll put it off of here, stopper that up, and we'll turn that heat off. Okay, next up, we have this molecule. And how do we classify this one here? This is also an alcohol, because again, if we check out our classifications that we ended with at the end of the hour, our classifications, in case you don't have it, if it has this OH on here, that makes it an alcohol. And so now with 4 carbons, when we look at where that's located, it looks like we have a CH3, CH2, CH. We have an OH up here, CH3 on the end. This here's an alcohol. We follow our rules for naming, and let's see. We drop the letter E off the alkane name. Well, we first of all need to know that alkane name. What is the alkane name? Butane. Good. Then we drop the letter E, replace it with OL. That's butanol. But now because there's more than 3 carbons, we have to number the position of this hydroxyl group. And so what number would we give this?
2.
It'd be a 2. And because we count in the direction that gives us the smallest number. If we count from left to right, we get 1, 2, 3. If we count from right to left, 1, 2. Again, we count in the direction that gives us the smallest number for that group. Then we go to the next one. And the next one is right here. If we write out that formula, we've got CH3, CH2, CH2, C double bond O, CH3. This one here would classify as ketone, right? This is a ketone. So if we look at the rules for ketones, again, ketones are right here. It says that we are going to count the number of carbon atoms in the molecule. So the number of carbon atoms that's in here would be 5. So the name of the alkane with 5 carbons is pentane. Then if we follow the rules from here, it says if it's a ketone, we're going to drop the letter E off from the alkane name, and as a ketone, we'll replace it with ONE. And in this one here, we do need to number the position of the carbonyl group. So we drop off the E, replace it with ONE. And we have to number this position. This is on carbon atom number 2. So we would call this one here 2-pentanone. 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 And then if we go down to the last one, right here, we write out its structure. We've got CH3, CH2, CH2, C double bond O, H. This one here's an aldehyde. Exactly, this is an aldehyde. So we check out the rules for aldehydes. And we see once again, we count the number of carbon atoms in the molecule. We write the name of the alkane. Name of this alkane would be? Butane. We drop off the letter E, and if it's an aldehyde, that tells us we replace the E with? Al. And then we check this further. Looks like we don't need to do anything else with this. Here, of course, is where pronunciation is important. This is not butanal. This would be butanal. Butanal. Oh gosh, you guys are not humorous at all. All right. Oh, you can't be humored. Any questions? See, they thought it was funny. Okay, so now, you might notice that as we look at some of these are numbered, like these two here are numbered, but the rules, for example, for carboxylic acids and for aldehydes, there's nothing here where we talk about numbering the position. So why would it be in aldehydes and carboxylic acids that numbers are not included? Any ideas? Yes.
Because those can only occur on an end of the thing.
Right, because they can only occur on the end. If we look at butanal, this feature, this carbonyl group, can only be on the number 1 carbon. And if we look at propanoic acid, this feature here can only be on the number 1 carbon. And because it can only be on the number 1 carbon, there's no need to number its position because it's always going to be in that end or terminal position. In the alcohols and ketones, we do need to number that position because that distinguishing feature can move somewhere along that chain in the molecule. In the case of ketones, if we go back and look at the general formula for ketones, ketones have a general formula of R, C double bond O, R. And so this carbonyl group is always going to be sandwiched between some alkyl groups and will never be on the end, so its position would need to be numbered. In the case of alcohols, this OH group could take on any sort of position in the molecule. Right here we're showing it on carbon atom number 2. But we could very well put it down here on the very end, in which case we would call this substance what? This would be 1 butanol. This would be 1 butanol. So again, we want to tell where this OH is located. And when it comes to alcohols, those that had lab yesterday already spent a little time with this, and we would have seen that when the OH group is in the 1 position, we usually write it off on the right-hand side. So we would, this one right here we're showing is 2-butanol, but we could very well write out a formula like this: CH3, CH2, 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 OH. And we see where this is located on the very end. In this case here, since it's attached to the first carbon in the chain, we would call this one 1-butanol. OL because it is an alcohol. So any questions on these here? Any questions on these? What's that? Okay. Then we'll wrap up by working the other direction. Let's say we have some names. And so now these were the names that were in your Socrative app quiz when you came in here today. We had something like propanol. That was the first one on there. Then your next name was 1-hexanol. And then the next one was butanoic acid. And then the last name was 3-octanone. So now if we have these names, we should be able to work in the other direction to give us the formulas. And again, in case you've forgotten them, you can pull these out. These are your functional groups, and these are the general formulas that tell us how we construct these. So the first key to writing out the structural formula is to classify them. So if we look at this first one, propanol. How do we classify propanol? What do we look at?
Oh, the 3-carbon chain.
Well, it's a 3-carbon chain, but how do we classify it first? Is it an aldehyde, ketone, carboxylic acid? What is it? Aldehyde. We tell it's an aldehyde because Al suffix. So if this is an aldehyde, we come back here and we say aldehydes have a general formula that looks like this. So we know that we're going to have this C double bond OH on the end. You can start by writing that out. That's C double bond OH. C double bond OH. And now we look at it as being propanol. The prop tells us there's how many carbons? There's 3. Remember that this counts as one of them. So if this counts as 1, then we need 2 more. And so we then put it in as CH2, CH3, and this would be the correct structure for propanol. We then look at the next one, and we see 1-hexanol. We classify it as an alcohol because the OL suffix. The OL suffix tells us right here that it is an alcohol. And this alcohol is going to have how many carbons? 6. And the hydroxyl group is located on carbon atom number 1. So if we were to write this out, we'd have CH3, CH2, CH2, CH2. That gives us 4 carbons. Here's 5 carbons, 6 carbons, and because it is an alcohol, it would end with OH. And that OH then again is attached to carbon atom number 1. Any questions on this one? Next we go to butanoic acid. We'll classify this one as carboxylic acid, which we tell from its OIC acid suffix. This carboxylic acid is going to have a total of how many carbons? 4. Bute tells us we have 4 carbons, and it's a carboxylic acid. So in case we have forgotten how to write an acid, carboxylic acids have this general formula. It's going to have this carboxyl group down on the end. So we can put in the C double bond O, OH in there, which we know it's going to have for sure. That, of course, counts as one of the carbons. And if it counts as one of the carbons, that means we need how many more? 3 more. And so we count backwards on this one. We'd have a CH2, CH2, and on the left-hand side we'd have a CH3. Remembering, of course, that your text also writes it with H3C on the end. That's another way of writing it. It represents the same thing It doesn't really matter which way you write that one here on the left-hand side, whether the hydrogens are on the left or on the right. Okay, then we go to the last one. This one here is 3-octanone. We have a suffix of O-N-E, which tells us this would be a ketone. And this ketone will have a total of how many carbons? 8. Be 8 in there. And the distinguishing feature of that carbonyl group is going to be located at carbon atom number 3. So in case we've forgotten what a ketone looks like, we come back to our general formulas. We have a ketone right here. Looks like we need to put a carbonyl group somewhere in the middle of that molecule. C double bond O. This, of course, counts as one of those carbons. It's going to be in the number 3 position. So in the number 3 position, we could put in a CH2, CH3 on the left-hand side. Then on the right, here's carbon atom number 4, 5, 6, 7, and 8. And this would be the formula for 3-octanone. Now, as you do your mastering chemistry, remember that your mastering chemistry, you'll have the structure drawing tool. If you've started playing with that a bit, that structure drawing tool would kind of come out something like this: 2, 3, 4, 5, 6, 7, 8 all together. You'd put an oxygen here on carbon atom number 3, and then your structure drawing tool in mastering chemistry also puts these terminal carbon, or shows these terminal carbons in here as well. So on mastering chemistry, it would look something like this here. But again, chemists write them either with or without these terminal carbons. The default, though, on mastering chemistry is to show those terminal carbons out here in the molecule. Okay, any questions on these 4? Any questions on these 4? Okay, then we're going to wrap up with a look at ethers. Ethers. Not ethers, but ethers. And don't ask me why we call these ethers and the other ones esters. Why this has a long E, I have no idea. That's just the way we do it. And the general formula for ethers, right here, ROR. So I have an oxygen sandwiched between 2 alkyl groups. So one example of that would be something like this: CH3, CH2O, CH2, CH3. Another example would be something like this: CH3O, CH2, CH3. So once again, we're looking at an oxygen atom. I'll color code these here. An oxygen atom sandwiched between 2 alkyl groups. Now, to name these, we come back to our rules for the nomenclature of ethers. And the rules tell us to name each alkyl group attached to the oxygen in alphabetical order, followed by the word ether. For example, butyl ethyl ether. If the 2 attached alkyl groups are identical, then we use the prefix di for the alkyl group. For example, dimethyl ether. So we come back here and we check this out. How many carbons here? 2. And here? What do we call a 2-carbon alkyl group? That would be ethyl. And because they're both identical, that tells us it should be diethyl, followed by the word ether. So this would be diethyl ether. Diethyl ether. And this, by the way, was one of the very first anesthetics. And back when I was in college, we would, in our A&P classes, If we had to anesthetize something, we would use diethyl ether to anesthetize our little creatures. Okay, and then if we look at this one, this here would be a methyl group. This here would be ethyl group. Then if we check out the rules tell us which one comes first. Ethyl, because we name them in alphabetical order. So the name of this would be ethyl methyl ether. So ethyl methyl ether. And say that fast 10 times. Ethyl methyl ether. Now as far as the names go, you'll see that we have spaces in here. There's a space here, a space here, space here. And going back to our carboxylic acids, we have a space in here. And back on our previous page, we have a space in here. So the only organic molecules where we include spaces in the names are carboxylic acids, ethers, and as you will learn in lab, so will the esters. And we will not be spending time here in the lecture class with esters because you have an entire lab devoted to esters. Go ahead and write out this one, and this is going to take us here to the end of our organic chemistry. Write out the structure for butyl methyl ether. I'll give you about a minute or two. Structure. Butyl, of course, means how many? 4. Methyl means 1. And in between the 4 and 1 would have 1 oxygen. And it looks like I need to move this a bit. Any questions on anything with organic chemistry? Anything that we've gone through, any expectations? Your worksheet. We pull out your worksheet. At this point, you should be able to complete all this worksheet. We will not be covering this in class. You will find this linked to D2L with the answers. The only one that you are not responsible for in here is number 15. We've run a little short of time, so number 15, you can cross that out. But if you're wondering what does a quiz look like or exam look like in organic chemistry, this is what it looks like right here. And then of course there'll be a few more things like we talked about general formulas of alkanes, alkenes, alkynes. We've talked about the terms saturated and unsaturated. We've talked about classifying them. But again, if you're wondering what does a quiz look like in terms of structure, looks something like this. So any questions that we have? Okay, so textures. Remember that the back row is for textures in here. Any questions? Okay, then we are going to move on from here, and we do have another quiz available on our Socrative app. And the next quiz that is available looks like this. And I have a demo set up here, and what I'm going to do here is I'm going to monitor the temperature of this heating of water. And I'm going to use Logger Pro like we've been using in the lab. And if you get logged on to the Socrative app, again, it's last name, first name. First question is going to be, at what temperature does water boil? So I actually have a series of questions that we're going to answer. And those questions are right here. So we're going to have a series of 7 questions that we'll look at. First one's going to be, at what temperature does water boil? Next will be, what is the temperature of boiling water after 5 minutes? Then after 10 minutes, and so forth. So what I'm going to do here is I'm going to give you a chance to look these questions over, and before you commit yourself to answers on the Socrative app, I'll give you about 3 or 4 minutes here to talk with your neighbor and see if you can come up with answers to these. And these are answers I am going to record this time here to see how well you've done. So I'll give you about 3 or 4 minutes. Let's turn to your neighbors and talk them over. So, get your answers locked in on this one. At what temperature does water boil? Label your answers with either C or F. Next question. What is the temperature of boiling water after it has been boiling for 5 minutes? Once again, label your answer with C or F. And right now, oh, I've not been collecting my data. How about that? I got to stop this. I'm going to put this out for about 700 seconds. And I meant to collect the data. Here we go. We'll get some of it out of here. Get your answers locked in. And we'll go to the next one. What is the temperature of boiling water after it has been boiling for 10 minutes? Once again, label your answers with either C or F. And we'll go on to the next one. What happens to water molecules when water boils? What happens to water molecules when water boils? Give you about 30 seconds. Give you about 10 more. Count down. 5, 4, 3, 2, 1. Next question. What is the primary substance found in the bubbles of boiling water? What is the primary substance found in the bubbles of boiling water? If you look at our water that's being heated right now, looks like we're up to about 90 degrees Celsius. Not quite boiling yet. So get your answers locked in. 5, 4, 3, 2, 1. Next up, is it possible to boil water without heating? If so, how? And then please note that adding a chemical isn't a possible answer since the process of boiling is a physical change, not a chemical change. Is it possible to boil water without heating it? If so, how? Give you about 30 seconds to get an answer locked in on this one. And it looks like we have some water boiling here. If we check this out, looks like the water is beginning to boil right around 98 Celsius. If we take note of what's happening to the shape of the graph, what can we see is happening here? Starting to level off. Starting to level off. All right, and then we go to the last one. Is the process of boiling or evaporation an endothermic process or is it an exothermic process? Is it endothermic or is it exothermic? Okay, and then you can, once you get your answers locked in, you can set down your phone because I am going to go through here and go through these answers one at a time. And we'll look at what we came up with for results. And first one here, looks like we have 100 degrees Celsius and 212 Fahrenheit for most of us. And as we are observing, where is it? Right here. Looks like we are pretty darn close. Now, this appears to be what the water is boiling at today. It's 98.6 Celsius and not 100. Any ideas why it's boiling at 98.6 and not 100? Yes.
Because if water is at 100 degrees, it's no longer boiling water, it is now gas.
Well, actually, that is not true. It actually is where a phase change occurs. Any other ideas? All right. It does boil at 100 degrees Celsius under a certain set of conditions. And that certain set of conditions is on average at sea level. So if we talk about a boiling point of 100 degrees Celsius, that is the boiling point on the average at sea level. And on the average at sea level, the pressure is 1 atmosphere. So when we talk about a boiling point of 100 degrees Celsius, a boiling point of 100 degrees Celsius will only happen when the pressure is 1 atmosphere. Now, of course, things can cause that to change. And one of the things that can cause that to change is the weather conditions. When the weather conditions, we have conditions of low pressure. Now you might see, I won't finish that sentence quite yet, but you might look at a package of cake mix or whatever. And on a package of cake mix, one of the things you'll always find on there is high altitude directions. And why would there be high altitude directions on there?
Because it's different than low altitude.
At a higher pressure, water is going to boil, not at a higher pressure, but at a higher altitude, the water is going to boil at a lower temperature. And part of the reason for that, and hopefully we've established here that that boiling point is going to remain relatively constant, and I'm guessing it's somewhere here right around that 98.8, 98.9 or thereabouts here for today. And I don't like to heat this too long because for whatever, these probes are not super durable, so I'm going to pull this out for right now and we'll stop that data collection and turn this off. But in order for something to boil, what has to happen is this. First of all, if we looked at water, let's say that we have this as a beaker of water right here. And the water sitting in that beaker. And on top of that beaker, you might remember, top of that water, what's acting down on the surface of that water is?
Pressure.
Pressure. And where does that pressure come from?
The atmosphere.
The atmosphere, exactly. So these would be the gas molecules that are acting down on that surface. Well, if we go up to higher altitude, that pressure is not as high because at the top of a mountain, there's less collisions occurring with the surface. There's less atmosphere above it. And because there's less atmosphere above it, there's going to be less collisions that are occurring with the surface. So if we maybe reduce the pressure down to something like this, with less pressure acting, that makes it easier for water molecules to escape from that liquid phase and go into the gaseous phase. If it's easier to escape, that means that the water is going to boil at a temperature that is lower under conditions of lower pressure. And if we're at a higher altitude, like at the top of a mountain, then we're going to have a case for lower pressure. Now, does anybody do any canning, or parents do canning, or know anyone that does canning? And what's one of the devices you use in canning?
You put the jars in boiling water to help seal.
Yeah, I use something called a pressure cooker. And in a pressure cooker, basically what you do is you seal up. It's basically a large pot. And the pressure cooker got some attention here with the Boston Marathon probably 3 or 4 years back. there was the bombers that set off the bombs, and they basically put all the chemicals inside of a pressure cooker. And part of the reason why they do it is it's a very thick metal. You can seal it up. And inside the pressure cooker, usually what you do, though, is you put this on top of a stove, you heat it up, and if the gases can't escape, then what happens is that the pressure builds up very high, and there's a ton of collisions occurring with the surface. And when there's a whole bunch of collisions occurring with the surface, that causes the boiling point to go up, because when we have all these collisions, it makes it more difficult for those water molecules to escape. And so the whole idea behind a pressure cooker then is we want to elevate the boiling point in order to do what? Anybody know why we can stuff? Yeah.
To make it last for a long time and kill all the bacteria.
To kill the bacteria, exactly. We want it to last a long time, so to kill the bacteria, we need to elevate that boiling point. And so we elevate it above 100 degrees Celsius, and that makes it more likely for that bacteria to be killed off. And also drives that heat further into the food to kill that stuff off. And many times in the previous history, whenever we did not properly kill off the bacteria, we wind up with some food diseases called botulism. And of course today botulism also has a good side to it for some people. Anybody know what we use botulism for? Well, it's also found in Botox. Okay, it has the name Botox. It's toxic. Okay, but you take small injections of it and it causes your wrinkles or whatever to disappear, stretches things out. But if you ingest botulism, you die, basically, if you ingest enough of it. So the whole idea of pressure cooking is to go ahead and kill off those bacteria and prevent botulism from occurring. So as we go through the remaining questions here and look at these boiling points, again, after it boils for 5 minutes, the temperature is going to stay constant at 100 degrees Celsius, or, like we saw, it would stay constant at about 90, for us it was about 98.8 or 98.9. And part of that reason is that if you have paid any attention to the weather the last 2 days, you notice that we had some really, really nice sunny weather. And the weather this morning, at least when I was driving in, looked like it was kind of cloudy and everything. And I saw some moisture on the road. And there was a lot of wind, as I recall, either yesterday or the day before.
Nice.
And that's usually an indication that change in weather is coming. And usually when it's fair and sunny, we have conditions of high pressure. And whenever we have cloudiness and rain, that's usually associated with low pressure. And so had we done this a couple days ago in here, very likely we would have seen a boiling point of about 100 degrees Celsius. But because we have a change in weather occurring here, we have conditions of low pressure, and with conditions of low pressure, what that's doing is it's reducing that number of collisions on the surface here and making it easier for that water to boil and escape. So even here in Coon Rapids, or anywhere you go, the boiling point will change depending upon the weather, depending upon the pressure that's out there, because that change in pressure will change the number of collisions with that surface of the liquid. Okay, so we'll go through here next. Again, same thing. Next question is, what happens to water molecules when water boils? And we checked these out, some answers. It vibrated really fast and wants more room, so it turns to gas. They vibrate faster. They move faster, and those are all good. Yep, they move faster. So that would be good. And I'd also add this one here. They turn into a gas. They turn into a gas. Next question was, what is the primary substance found in the bubbles of boiling water? Well, the primary substance in the bubbles of boiling water is... It is water. Because what type of change is boiling? Chemical change or physical change? Physical change. So if it's a physical change, that means if we start with water, we better end with water. And I was going to demonstrate that and I forgot, so whatever. I don't have the water boiling anymore, but just think about this. If we produced hydrogen gas, and we didn't do the hydrogen in lab this year, but we did see hydrogen day one in here, and hydrogen does what in the presence of a flame? Explodes. Would it make sense that we're going to create explosive gases by boiling water? Doesn't make sense. You did do oxygen in the lab. Remember that oxygen causes things to burn more vigorously. That wouldn't make sense either. If we're boiling water, we don't see flames all of a sudden go rushing around from any oxygen being produced, and that's because
It'd be difficult to have bombs.
it isn't. Okay, next one. Is it possible to boil water without heating it? And answer that question. Yes, no. Liquid nitrogen was boiling. Okay, but this is water now. And so what I'm going to do here, I noticed somebody suggested put it in a vacuum. Who was this? All right. Very good. And what I'm going to do here is I am going to take out my vacuum pump, and we're going to boil some water. And I'm going to come around here. And I don't want to break that, so I'll set that down. And I have not used this for a while, but we'll go ahead and hook this up. First of all, I'll take this off so we can see how the vacuum pump works. I need to get the hose on here first. And I brought out a larger flask. That larger flask has a larger piece on it, so I don't want to break this. Let's see here if I can get this on here.
Do you have a smaller one if you can?
I do. But the larger one would be more fun if I can get it on here. It looks like I might have to go and get a smaller one. So when we do that, I'll be back in about 1 minute. Smaller. So we'll see if this works. Get this on here. And I don't know, somebody must have stuck a smaller hose on here. Here we go. You can fit this one on. So, nice cookie maker, right? Alright, so what we're going to do is we're going to take this off of here and we're going to put some water inside of here. And this is really a lot more fun with a larger flask. I don't know what happened to the hose on there. And of course I have the wrong size stopper here now too. So I am going to try once again to get this on here, because I'm stubborn. And I think I can do it with some of this stuff that's on here. I have a little bit of
Vaseline.
what's a glycerin lubricant on here. And you need to be careful here so you don't wind up. There we go. Do I have it on? I think I do. There we go. Much better. So we're going to pour the water into here. And of course I should have kept this over here, right? So I can't get all the water in. Now this type of flask is called a sidearm flask. And it's called a sidearm flask for the reason I hope you can see. It's got a little arm off the side. And now I can go ahead and put this in here. And I need to get the thermometer back down where it was. We want to measure the temperature of that liquid. I need to get in it a little deeper. There we go. And I'll put this back over here. And in order to do this, since Gwen, you did guess correctly, let's go ahead and have you measure the temperatures and just check out what the temperature is of the water here right now, if you can.
It looks to be 24.5.
About 24.5. We'll turn on the vacuum pump and watch what happens to this. Now remember, what we're doing is we are reducing the pressure above the surface. And now the water is beginning to boil. Now what do you think's happening to the temperature? Gone up or down? Or stayed the same? Stayed the same. And to check that out.
It's not hot whatsoever. It's still plenty. Actually, the temperature went down a little.
Yeah, it will. And so the temperature right now is how much?
It's about 23.5.
About 23.5. And actually, the longer that I allow this to boil, the more its temperature is going to actually drop. And part of the reason why it drops is this. First of all, if you think about it, if molecules are going to escape from this liquid, which ones are going to escape first? The faster ones or the slower ones?
Faster.
Faster ones. It's just like if somebody's chasing a whole bunch of people, the one that's going to escape first is going to be the one that is the fastest. So molecules are the same way. The ones that escape first are the fastest. And of course the fastest ones are associated with the ones that have a higher energy or higher temperature. And that leaves behind the slower ones. And as a result, the longer that you heat this, the more this temperature is going to drop. And so this brings up something really interesting here. And I'm going to take this to the next question because it turns out there's another way we can boil this, which I'm going to show you in just a bit. But if we look at the next question here and we ask ourselves, is the process of boiling or evaporation an endothermic process or exothermic process? The correct answer is an endothermic process. And one of the ways that I can show this here, and if you want to experience what I'm doing here, I'm going to walk around, and what I have in here is some isopropyl alcohol. And isopropyl alcohol is the alcohol found in rubbing alcohol. And so what I'm going to do here, for anybody that wants to, set your hand out, and I'll put a few drops on there, and just blow over the top of it and see what you feel when it's on there. And if you don't want to do this, don't set your hand out. But again, I'll put a few drops on your hand. And if you have a cut, please don't set your hand out. Okay. And just see how it feels when you do this. Again, this is isopropyl alcohol. If you don't want to do it, don't set your hand out. Anybody down here? And when you blow over the top, how does it feel? Kind of cool. And it feels cool because, once again, the molecules that escape first are the faster ones. It leaves behind the cooler ones. Now, how do you and I make use of that?
Sweating.
Sweating, exactly. When we sweat, what happens is our body is releasing that water, and we release that water, so once that water gets on our skin, that water will evaporate. And as it evaporates, the molecules that stay behind are the cooler ones or the slower ones, and that winds up cooling us off. And so the process of boiling or evaporation is an endothermic process. And the same is true even if we are heating it. If we put a beaker on top of here and are heating this, you might not think that that is being absorbing energy because after all you're putting heat into it. But if I take this off of here, then what happens to the boiling? It stops. So I put it on here, it has to absorb energy out of the hot plate in order to cause it to boil. And if you actually were to look at a hot plate, you maybe even do this when you see your stove at the home. You put a pot of boiling water on there and you might actually see those coils actually cool down a bit. You take that pot off and those coils will heat back up. And so even your stove works that same way. Even though it's just at a higher temperature, it still has to absorb heat out of there in order to cause it to boil. And some other ways we make use of this actually might be in your air conditioner. Okay, so I'm not much of an artist, but let's say that this is my house right here. And in the house, where does your central air unit sit?
On the outside.
Sits on the outside. So this here you might have being your central air unit. And your central air unit has a pipe that runs into your house, and inside of there's a whole bunch of coils. Those coils sit inside of your furnace, and then it's pumped back out here to the central air unit. Well, what happens in here is two processes. That pipe is very tightly sealed. And inside of the central air unit is something called a condenser or compressor. And I know that a HVAC technician would distinguish between the two. We don't need to here in this course. But basically, what the purpose of this is to compress or condense a gas. And if you ever stood outside and felt the central air unit, how does the air feel that comes off the central air unit outside? Feels really warm. And of course, if you're on the inside, the air coming out of there feels really cool. And that's because we have two processes going on. What will happen is that when the liquid is sent into the house, there's a liquid that's out there in the central air unit. That liquid goes into the house, and as it goes into those pipes, that liquid will evaporate. And as it evaporates, the process of evaporation, as we saw, is an endothermic process, which means it will absorb heat from the surroundings. So in that case, inside the house, it's absorbing heat from the house. And as it absorbs heat from the house, then, it causes that liquid in the pipes to turn into a gas. That gas gets sent back out to the central air unit. And once it gets sent back out to the central air unit, that gas is compressed back into a liquid. And it gets compressed back into liquid. That process is exothermic, and it winds up giving off heat to the surroundings. So we separate the two processes. The endothermic portion, the evaporation, occurs inside, and the condensation occurs outside here, which is an exothermic process. And actually all air conditioners work the same way, whether it's a central air unit or even if you have a wall unit. And the whole reason why your air conditioner has a piece that sits inside of your house and a piece that sits outside of your house is because the piece that's inside of your house is absorbing the heat, and the part that's hanging out is giving off the heat. And so we separate those two processes. Refrigerator works the same way. A refrigerator is basically something that sits, your refrigerator basically sits right around this unit. So your refrigerator sits here, and there's a little piece, a compressor condenser that sits right in the back here. If you ever feel the air that comes out from underneath or from the back of your refrigerator, how does that air feel? It's warm. And that's because your compressor, your condenser sits outside your refrigerator there, and that's where the condensation is going on. And inside the refrigerator, there's some coils. Very often they cover them up with plastic so you don't see them. But on the inside of the refrigerator, that is where your evaporation is occurring. And so by separating the two processes, then we can wind up cooling down our food. And so to keep all these processes straight, if you make a diagram, something like this, solid, liquid, and gas, putting the lowest energy one on the bottom of the three phases, which would be a solid. So if you kind of stack these up here like this, so again, solid, liquid, and gas in terms of energy, if you go in this direction here and you are absorbing energy, these processes here are endothermic, and anything here that goes in the reverse direction is an exothermic process. So that means, and we're going to go over by about 1 minute here today, I think. That means that if we convert a liquid into a solid, converting a liquid into a solid is called what?
Loses energy.
Yeah, but I know it's exothermic, but what is that process called? If we take liquid water and we turn it into a solid?
Freezing.
It's called freezing. The process of freezing is an exothermic process. And so, if we were to look at an example of this, I put this up here in your D2L for today. Here's an image that shows spraying some citrus fruits with water. And you spray citrus fruits with water in order to prevent the fruits themselves from freezing. And if you were ever to go down to the south when the weather gets really cold, you'll actually see where they are spraying those fruits, whether they're strawberries or citrus fruits or whatever, with water. And you'll say, well, what in the world are they doing? You'll see all the ice hanging down there. Why are they spraying it with water? Well, the whole idea is to prevent the fruits themselves from freezing. Because as the water lands on the fruit, the process of freezing is an exothermic process. It releases heat to the surroundings. In this case, the surroundings are the fruit. And so while the water itself freezes, the fruit itself is prevented from freezing. Yes?
Is that why when I have seen fields covered in frost because of sprinklers and it was below freezing and then the frost melts and the grass is, oh hey look, I am not dead for some reason. Is that why?
Exactly what it is, exactly.
That never made any sense because
Yes.
if it's literally covered in ice, it shouldn't have died.
Yeah, but it's because you have the sprinklers out there for that very reason, to prevent the stuff, the crops, whatever, from freezing. So, with that, I have one demo here to wrap things up here for today. And this demo goes back to this question right here. Is it possible to boil water without heating? And so, you might remember how we started this class today. We started it with this beaker or this flask sitting on the hot plate, and remember I heated it long enough so I would remove all of the air from here. So the only thing I should have in here right now is water in the liquid phase and water in the gaseous phase, and I seal it up nice and tight so no air could get in there. Now if you feel it at this point, it's still warm, okay, still warm, but it's not super hot. But what I'm going to do here now is I'm going to turn this upside down, and I'm going to take this ice and I am going to get this water nice and cold, and then I'm going to come over here and I'm going to pour this ice water over this flask. And you can see here that I can cause the water in here to boil by pouring the ice water over the top. Now, how does this work?
Because the ice
As I pour this water over the top, that's causing the water that's in the gaseous phase to turn into a liquid. Once this water in the gas turns into liquid, that causes the pressure in the space up above here to go down, as it goes down, then the water can boil at a lower temperature. And so we can boil water by pouring ice water over the top. And sometimes I need to hang on to this because
Jump.
it likes to jump,
Why does it jump?
because it will super boil or super cool. And I'm going to have to bring this out here again on Tuesday once this gets down to room temperature, and we'll see if we can get this to boil in on, not Tuesday, this would be Thursday. So, all right, have a good one. We'll see you later.